Okay, we're going to finish up. The last important graph algorithm is going to call minimum spanning tree. A good example they have here is a company wants to shut down the maximum number of connections and still be able to fly from one city to another. Let's say they need to cut down the number of airplanes, but they still want to be able to service everyone at the same time. Which connections can you actually cut? And the minimum spanning tree would be doing it by cutting it, and your final graph will be of minimal weight. So with this graph, don't think about the weights right now. Let's just see if they're connected. Could we cut 3 to 4?
Yeah.
Yeah, because you could still get to there via other things. So 3 to 4, 1 to 5 you could cut out, probably 2 to 5 as well. And then you just have to go around this ring and then maybe from 0 back to 2. And that would you'd still have everything connected. Your users might not be too happy because to go from 5 to 6, you'd have to fly 1, 2, 3, 4 layovers. I don't think people would like that. But you wanted to cut the number of routes, so you knew that cost was going to happen. So here's some other examples of minimum spanning trees. It's important to look at this and think, are there any other connections I could cut? Well, B, hopefully, is most obviously no. But the rest of them, kind of take a minute to look at it, but you can't cut anything else from this graph. All right. Hopefully from last time you've noticed there's a lot of definitions or terms with graphs. I'm going to go over them, but only tell you about the ones that actually matter. But for this class, I guess weighted tree is the only one that matters. So a free tree is a simple graph such that if U and B are two vertices, there's a unique path from U and B. All right, they call it a free tree. So in other words, there's always one path from one tree to another. There's no secondary path. Does that also mean there's no loops? Or no cycles? Well, let's think about this. This is why graph theory is so interesting. Are there any cycles here? Are there any loops?
No.
No. Now, if I made a connection from 3 to 1, then there'd be a loop you can go around like this and back to 3, right? Okay. So there is a loop there. But if this tree is minimal or free, are there any loops here or cycles? That's what it really means, pictorially or conceptually. You have no cycles here, no loops. A rooted tree, this particular vertex is designated at a root. Sometimes in graph theory, it's easiest to just consider some node as a root and then treat the rest of it like a tree. If a tree is free, then you can just pick a node to be the root, and now you have a tree. And then a weighted tree, it has weights assigned on the edges. We're used to that right now. Okay, a spanning tree. Oh boy, wow. If T is a subgraph of G such that V of T is equal to V of G, all vertices of G are in T, okay, it has to be connected. So, spanning tree is what we're talking about here, where you're connected to every node. If you're at one node, you can get to every other node, and of course, vice versa. What algorithm would you have to run in order to confirm that a tree is connected? Well, if it's undirected, meaning you have a connection both ways, then yeah, you just do a traversal and see if you can get to every node, and then you're done. But if it's directed, what do you need to do? You gotta do depth first on basically every node. I'm just trying to get you all thinking with graphs. Minimum spanning tree, the spanning tree in a weighted graph with the minimal weight. Whew. All right, there are two well-known algorithms, Kruskal's and Prim's. We're going to do Prim's algorithm for the end of this class. You basically build a tree iteratively by adding edges until a minimal spanning tree is obtained. So it's actually, the idea behind the algorithm is not complex, but you're going to have to store a lot of information while you're going through this algorithm. So you'll be using the STL bit. Yep, keep this going. So you start at some vertex called the source. Each iteration you add a new edge that does not complete a cycle to the tree, and you want to also add the minimum weight. Okay. This, I think, is best done by going through an example. Let's pretend we have this, as we see on the board, which was given earlier. Is that a minimum spanning tree? No. Is it least connected? We can get from one node to any other? All right, so we got that. So we can build a minimum spanning tree from this. Okay. Prim's algorithm. Upper left is where we begin. We begin with the nodes that we are currently visiting. We're going to start by visiting node 0. Let me use a pointer so you all understand what I'm talking about. Start visiting nodes of 0. You probably want to make this an array. And then a list of edges. Currently nothing because we haven't added an edge yet. And then the extra nodes we want to go to. All right, so we're at 0. Which nodes can we go to? 1, 3, 2. Which one do we want to add?
3.
Going to 3. Why is that? The least amount of weight. So that's the least from 0 to 3. So next iteration, we add 3. We have the edge is 0, 3. So you're going to have to make a list of pairs here. Then we have the list of nodes. This total nodes. I guess it's just all our nodes. 3 should not be in this list. So that is an error. 3 should not be in the list because that's a list of nodes you need to visit. So you have 0 and 3. Notice that they're only evaluating 0 to 1, 0 to 2, and 3 to 4. Why aren't they evaluating 0 to 3? We already had it. So keep that in mind when you run this algorithm. Don't add the same edge more than once. But also realize that they're now evaluating all the edges. Now it's actually not the edge that the reason why that's cut off. Can you actually, or do you know why that edge is removed? It's not because it's already been added in particular. It's more the fact that 3 has already been added to your list of nodes, so you don't want to evaluate that edge. So you have 0 to 1, 0 to 2, 3 to 4. Which one do we want to add? 2. Why is that?
Least.
Yeah, it's the least. So now we have 0, 2, 3. We have the edge 0, 3, 0, 2, and the nodes left is 1, 4, 5, and 6. So we evaluate 0 to 1, 3 to 4. We also, oh yeah, not that one yet, sorry. 0 to 1, we don't do these two because 2 and 3 have already been added, and 3 to 4. And we've added 2, so we're also going to do 2 to 5 and 2 to 6. Which one do we add?
6.
And the reason for that is? All right, we're doing great. So 0, 2, 3, 6, these are the 3 edges we've added. The nodes left is 1, 4, and 5. So we have 0 to 6, we have 3 to 4, or actually, sorry, they have 2 to 5, 3 to 4, and 6 to 1. Notice that we're evaluating 2 different ways to get to 1. Which one do we add? That has a weight of 6. 4, right, sorry. 1 to 6 with a weight of 4. So the nodes we've added are vertices, 0, 1, 2, 3, 6. We have the edges and dotted lines here. All right, we're evaluating 0 to 1, 3 to 4, 2 to 5, and notice that 6, yeah, we're not evaluating a thing there. 1, why aren't we evaluating 1 to 0? That's the question.
Because we're already at 1. We already included 1.
Not because we've already, well, yeah, we've already included 1 and we've already included 0. So the 2 endpoints are already included, so we don't evaluate that edge. Even though it could have been the least. It would not have been evaluated. That's very important. You'll get a little trick. Make sure you put that in your code, because that's, I think, the tricky part to this algorithm. But which one of these is the least? 1 to 4. So we add 4, 1 to 4. Here are edges. Last node left is 5. So you're really just evaluating everything to 5, which is 2 to 5 and 4 to 5. And the least is 7. So you add that, and then you're done because you now have graph vertices. Yeah, those are your vertexes, and those are your edges. Any questions about this algorithm? No questions? Quick summary. Remember, a graph is first a pair of vertices and edges. The vertices is a node. Not a node, but a pair. Not a pair. What is a set? I mean, it's a pair of vertices and edges. The vertice is it's not one vertice, it's multiple vertices, or a list of vertices, a set of vertices. And the edges is, mathematically speaking, we consider it as a set of pairs that say the source and destination, or triplets if we're adding weight. This is the mathematical definition, not the coding definition. You gotta keep the two separate because this is how we write them down and evaluate them on paper, and that's how we actually do it in code. You have to realize they're the same thing, but it's important that you're going to evaluate them differently because when you go talk to a mathematician, he's doing it this way. This is just how you make it happen, Cap. Happen, Cap. Make it happen, Cap. So undirected are ordered pair, unordered pairs. In a directed graph, you have the source and destination are ordered. The subgraph, that should be obvious, two vertices. Yeah, are adjacent if there's an edge between them. We've talked about loops and cycles. Shortest path gives the shortest distance from one node to every other node. In Dijkstra's shortest path, it should say. In a weighted graph, we usually have everything with non-negative weights. Otherwise, it wouldn't make much sense. It's called a spanning tree if T is a subgraph. Okay, that's a mathematical way of saying they're connected. All right. Any questions about graphs? How do you think graphs compare against trees? More complicated, less complicated?
I'd say more complicated.
Why would you say more complicated? I agree.
Because,
I agree.
Because with like a tree, you don't really have to keep track of like all the infinities and crap like that.
Mm-hmm.
Like you don't have to do that with the list one either. But like if you're using a matrix, like you have to keep track of everything you can't visit.
Right. So if you're doing a depth first reversal on a tree versus a graph, which one was easier to code out? The tree, right? And that's going to be the case for most of the time. The algorithms for a graph are more complicated, but a graph can represent a lot more than a tree can. I think that's probably one of the high-level data points for this presentation. Okay, any other questions about graphs? All right.